All right, let's go ahead and get started. Okay, so I've collected homework 3B. Homework 3A has been graded, and if you didn't pick that up, you can grab it after class. We only have one more assignment until our first midterm exam, and so homework 3C is due on Thursday the 29th, and that's the same day of the exam. And so on those problems, obviously you're not going to have that assignment graded before the exam. If there are certain problems you're not sure whether you did it right, then what you can do is stop by my office and we can go over it together, or send me an email, and I'll confirm whether you've done the assignment correctly, if there's any problems you need to check on. So for the exam itself, it's scheduled just during our class time, meaning you'll have 75 minutes. And the equation sheet will be provided. If you'd like to look at what that equation sheet is, it's already posted on MU Online so that you can see where the formulas are on the page and try and familiarize yourself. It does not include variable descriptions. And so you're going to have to remember, for example, that delta H means the vertical distance from the water surface to some point of interest, or to the centroid if it's a hydrostatic forces type problem. So you need to know what gamma means. Gamma's unit weight, and so on. The coverage will be through class 11, which is the Tuesday prior to that Thursday exam. And so any questions related to these announcements or the test itself? If I'm not mistaken, the exam is worth about 20% of your grade. Yes? Well, you can look it up. It's posted online. So it's equations, the centroid formulas, for example, area moment of inertia formulas, but not the names of variables. So I don't define them for you. I don't remember, honestly. If I gave you a problem where you needed to do unit conversions, like, for example, if I gave the information in traditional units and I wanted the answer in SI, then I'd probably build those conversions into the problem statement. Other questions? Okay. Well, today we're going to continue talking about hydrostatic forces, but it gets a little more complicated because we're going to take a look at what happens when the surfaces are curved rather than flat. And in order to do that, we have to have a good understanding for what projections are. It just seems like the heater kicked on in here, doesn't it? Very warm. It's like a cyclone in my office. The fan is going full speed all the time. I can hardly keep papers on the desk. The fan is blowing so hard. All right. So an orthographic projection is a 2D representation of some three-dimensional object. And we'll have views from each side. So think about, for instance, the old trick of making shadows look like something that, obviously, it looks like a rabbit, but it's not a rabbit, it's somebody's hands. But if you think about what the 2D representation of that curved surface is, one way to visualize things is just to think about what if a light was shining from one side to the other, and what would the shape of the shadow be that was cast. And if you can keep that in mind, just thinking about the shape of a shadow, then these kinds of problems become very easy. This object is far more complicated than any of the shapes you'll have to deal with when it comes to curved surfaces, finding the pressure on them. But here's an example of a curved surface. It's a gate that is below the water line some distance, and when you are presented with a picture like this, what you'll have to do is break the shape down into pieces and ask some questions about the shape. And so here's some of the questions you can ask about the curved surfaces you need to find forces on. So for example, what is the shape? And often it won't tell you directly, like with a little text box. You'll just have to kind of infer from the drawing what it is. And in this case, it's a quarter circle. That curve is a quarter circle, just by inspection. You don't have to get out any kind of a ruler and make sure. You can just kind of, if it looks like a quarter circle, it's probably a quarter circle in drawings like this. That's not to say that it's necessarily everything is to scale. It may be that from the dimensions you're given, it could be a radius is one thing, and then the depth to the edge of the circle is another, and it's not necessarily 1 inch on the drawing equals 1 inch in reality. You have to go by the dimensions that are provided. And so if you wanted to find out how deep is the curved surface, then what you could do is reference some starting point. So the beginning of the curved surface up to the water surface, or the bottom edge up to the water surface. Asking the radius of the curve is important because in problems like this, you're going to have to find both vertical and horizontal forces. And this is different from what you were doing with flat surfaces. When we had flat surfaces, there was just kind of like a single procedure that led to the one hydrostatic force equivalent that's acting on the shape. Here, you'll find that one equivalent hydrostatic force component by finding out the weight of the water above the curve, and then the horizontal forces that are also acting on the curve. And so, for those reasons, we need to know the radius of that shape, even though ultimately we'll think of its projection to find the horizontal forces. You still need to know the radius of this shape in order to know the height of the projection. So here are some dimensions that we can answer those questions. Okay? From the dimensions, you can tell that this has a radius of 2 meters. And so the distance CB is 2 meters, but CA is also 2 meters. Even though it doesn't say it directly, what you should be able to see in this drawing is that if you follow this radius down, then once you get to A, the distance CA is 2 meters. So location A is 6 meters under the water surface because it's 4 meters from this beginning edge B to the water surface, and then an additional 2 vertically down to A. All right, so it's a quarter circle. The depth, the beginning of the curve is 4 meters. That's provided from the drawing. You can see just by inspection the radius is 2 meters. And then labeling points like this, even if the drawing doesn't provide them, you'll sometimes have to draw these dashed lines yourself. The drawing that would be provided in the book maybe would look like this. And so putting those dashes in yourself allows you to break the water above the gate into components that are easier to find the area and volume for. I don't know if there's a formula for a shape that looks like a quarter circle at the bottom and then a rectangle. Not that single shape, but I do know the formula for a circle, and from that I can find the area of a quarter circle, and there is a very easy formula for the area and volume of a rectangle. And so that's why those dashed lines, even if they're not in the drawing, it's a good technique for you to try and break it up into pieces, whatever shape you're presented with. And then once you have drawn the dashed lines, you can come up with a labeling system to make it obvious for the grader or whoever's looking at your solution, maybe yourself, trying to remember it sometime down the road, making it obvious what pieces refer to what calculations. So tying the drawing and the calculations together with the labels. So any questions so far about these basics of how to see the problem from the point of view of the drawing that they give you? We'll look at a couple of these, not only in the examples, but I also have a preview of a couple of the problems you're going to be solving on the next homework assignment. So this is more about just visualizing the problem. We're not yet to the calculation stage, but what we've drawn onto this diagram are the forces that are relevant to the gate itself. Now, here's the labels, but before we go through the labels, just try and think about this FV is representing the weight of the water that's in element D, C, B, E. And so if this is 1 meter into the page, so that's a distance into the page 1 meter, then we're going to have a rectangular element of water, and it has dimensions of 2 by 4 by 1. And the weight of that water, if we multiply the volume by the unit weight, that gives us F sub V. And we follow the same approach with finding the weight of the water in this quarter circle. W, the weight of this water, is it's an element that I guess you could say is pie-shaped. It's a quarter circle that has a 1 meter thickness. And so we can find the volume of the water just by knowing the area of the quarter circle, then multiplying that by 1 meter, and then we can find the magnitude of the weight of the water by multiplying that by the unit weight, 9810 newtons per meter cubed if it's water. So far so good, right? The vertical forces are easy. It's just the weight of the water. Well, this F is an external force that would have to be applied to this gate to withstand the forces that are acting on it so that it doesn't fall out of place. And so the vertical component of F is just simply equal and opposite to the sum of the vertical forces of this rectangular element and the vertical forces of the quarter circle element. So that's the vertical component of F. The horizontal component of F is because not only is there water above this gate, but the water pressure that's pushing from the side also creates additional force that has to be counteracted. And so F sub H is the horizontal forces. So here are all of those definitions that we've just been talking about. The magnitude of F, the resultant force that has to be in place to resist the hydrostatic forces, there's two pieces to it, just the sum of the vertical and the equal and opposite of the horizontal forces. All right. So we're all on the same page so far. Let me ask you a question. Why do you think they've chosen to represent F sub V, the location that it's at? Why did they put it in the middle? Is there anything we should understand from the fact that they put that arrow in the middle and not a little bit to the left or a little bit to the right? Okay. So the centroid of the volume. So in terms of area, the location of the force, the location of the equivalent force, they've chosen to put in the center. It's not to the left, it's not to the right. And the center of volume, it's probably half the way in to that 1 meter thickness of the element. But since it's just being represented in 2D at this point, we can't see how deep into the shape that is, but we can see the left and right aspect of it. Okay? But what about the location of W? Why isn't it in the middle? What? The middle, okay. So my frame of reference from this one made me think that this is the middle. And so when you say it is in the middle, what do you mean by that? Can you elaborate? Okay. Yeah, this quarter circle has a center of area that's to the left of the center of area of the rectangle above it. So think about this little shape that is to the right of the quarter circle. That's not contributing to the location of the centroid. And so the center of area is to the left of 1 meter away from B. 1 meter away from B is where this F sub V is located, but it's more than a meter from B out to the location of W. So when we find the net location of these vertical forces, we're going to have to average those two locations. We're going to have to say that, like, when you combine them together, when you combine W and F sub V, the resultant force is going to be somewhere between the two. Anyone have an idea of how we'll combine them? Will we just take a simple average, or is there something better that we can do? Any thoughts about that? That would be one approach, yeah. I mean, related to that is just a weighted average. You say the location of this F sub B, and you weight it by the magnitude of the force, and then the location of W, which we can calculate, and it's weighted according to the magnitude of W, and you come up with a weighted average of the two. So we'll take a look at that as we solve this example. Okay, so here is the example, the first one we're going to work in class today. I've already told you that the FV and the W are easy. It's just the weight of the water. Now, we haven't talked a lot, though, about the projection of this shape. And you need to think about the projection of that shape before you can solve step one. Step one is to find the horizontal force. And this is what it's saying here in the parentheses. It says, find the horizontal force as though that force is acting on the vertical projection of AB. All right, the vertical projection. So we already agreed that this is a curved surface, and we could think about it as maybe akin to a piece of paper. Here's a piece of paper. It has some 1 meter width, all right, and so it has been curved like this. It was probably a metal gate to begin with, and it was bent into a quarter circle shape. So the vertical projection is, what is it going to look like if you view that curved surface from the side? So here's the curved surface, it's curved. What does it look like when you view a curved surface from the front? It just looks like a rectangle, right? What about a sphere? When you've seen pictures of the Earth from the moon, what does a sphere look like? It's just a circle, right? So that's what we mean when we're saying the projection is, what does the shape look like when you're viewing it from one direction? Because the hydrostatic forces that we're interested in are acting from the side. We've already accounted for the vertical forces by this weight of the water idea. And so now we have to account for the hydrostatic forces that are acting horizontally. And so in step one, you're going to pretend that this gate is actually just a rectangle. And the shape of that rectangle is 1 meter wide and 2 meters tall. All right, so I'm going to pause the recording, stop talking, and allow you to solve. I think you can get steps 1 through 5, where Fx and Fy are the sum of the vertical and horizontal components. All right. Some of you have a better eye for detail than me. In the problem statement, it says it's room temperature water. I overlooked that when I was preparing this solution, so I just used the standard default unit weight of 9810. But those of you with the fine eye for detail noticed that it said room temperature water, which would be 9790. So I'm going to remove that so next time my solution is more correct. But kudos to those of you who noticed it. All right, so the answers you get are going to be slightly different than what I show you on screen because of the difference in unit weight. But for now, it's the procedure that we really need to nail down. Okay, so the horizontal force, the projection of that curved gate is a rectangle with the shape of 1 by 2. And so we find the depth of the centroid of that shape is 5 meters. And the area of the shape is 2 meters. And from that we get the hydrostatic force, which is 98 kilonewtons, using the wrong unit weight, or 97.9 for those of you with the, All right, so any questions about the horizontal force as you were working through that one? Okay, then the vertical forces are just the weights of the water for the two elements that are above the gate. And the two elements are this rectangular box element and then the quarter circle pie-shaped element. And we can find the weight of water in both of those by just multiplying the volume by the unit weight of the fluid. So, everybody happy? Yeah, you look happy. That's how I could tell. All right. So in step 4, we're just adding up the horizontal force components, and so the external force we have to apply to resist the water pressure on the gate is going to have a magnitude of 98.1 kilonewtons, and the vertical force is just going to be the sum of these two vertical forces that were down. We obviously have to push up to keep that gate in equilibrium. And so the magnitude is 109.3 kilonewtons for the vertical forces. And then we can find the resultant force by the square root of the sum of the squares. And so the overall magnitude of the external force that is applied is 146.9 kilonewtons. Okay. Some of the homework problems, that's as far as it'll take it. It will just ask you to find the magnitude of the forces. Sometimes, though, it'll ask you to find the line of action, which means the location of the forces. And so that you're prepared for questions like that, let's take a look at, in step 7, if we go back to the problem. Now, don't worry, I'll come back to this solution if you're copying a few things. So here, the line of action for F sub h. What that means is find the YCP. So for the horizontal force component, obviously the location of the force is below the centroid. And we've done problems like that before. And in fact, this is going to be an easy one because since this is a vertical projection, it's going to be vertically oriented. And so what's the simplification when you've got some sort of a vertical flat object that you're finding the YCP for? Good. Delta H and Y bar are the same. So that'll be nice for when you're solving the YCP. What about area moment of inertia? Do we have the formula for area moment of inertia of a curved gate? We don't care that the gate is curved because it's really the vertical projection that we're continuing to work with. So it's just a rectangle. And we do have a formula for that area moment of inertia of a rectangle. I is AB cubed divided by 12, which is what we're going to need as one of the components for YCP. Which is A and which is B as far as that vertical projection. If we go over here to this side of the board, so what's A and what's B? Okay, A is 1, B is 2. Great. All right, so I think you can solve for YCP, and then the line of action for where the vertical force is located, the combined vertical forces. So it's going to be that weighted average or the moment analysis approach. So what I've drawn is the two components of the elements, and F sub B is in the middle, W is to the left of this 1 meter mark. And here's the formula for the area, for the centroid of a quarter circle. The formula is 4r divided by 3 pi. That'll allow you to calculate how far from C W is located in the direction of from C towards B. You can find out where the location of W is and then try and come up with a weighted average to say, you know, like this overall vertical force, where is it located? So that's the direction we're headed for both step 7 and step 8. So I'm going to stop talking again. I'll bring the solution to the first part of the problem up and turn you loose to start finishing the final steps. It doesn't matter. You can solve this problem from the basis. Mm-hmm. Yeah. So 5.0667. Everybody on board with that value? for finding the location of the horizontal force. Yes, question?
For like the location that we have for 8, is that from like what reference point?
The location of what?
Like for number for 8.
Oh, step 8. Okay.
Like from what reference point is that?
You can, this CX is referencing from the left. So you could find that amount and then subtract it from 2 and then have your point of reference be the right edge of the quarter circle. Not really, no. As long as you know what the starting point is for those measurements. But think of it this way. F sub v is bigger than W, right? If we go back to the magnitudes, F sub v is 78 and W is only 31, roughly. So F sub v is in the middle and W is to the left of the middle. But since this weight is only 31, it's not going to take the average too far to the left. I mean, the average location is going to be somewhere between W's location and F sub v's location, but it's going to be more towards the center because F sub v is so much larger. So over here on this opposite board, I've given you just sort of like a conceptual formula for a weighted average. And what the concept of a weighted average is like the bigger something is, the more it counts in the average. And so since the magnitude of ABC is relatively small, then its overall distance from C isn't going to count as much as the overall location and magnitude of piece B, C, D, E. And so the way that we do that weighted average is you multiply the location by the magnitude for each component and then divide by the sum of the two magnitudes. And that seems so abstract until you actually start looking at the real numbers. So let me bring those on screen here. All right. Yeah. No.
Is the weighted average derived from like moment analysis?
Not in my mind. I mean, this example is found in your textbook, and they use a moment analysis approach to it, but honestly, that never really made any sense to me. I know what a weighted average is, and you know the middle location between the two. So I solved it from this idea of a weighted average, but you know it can be solved through moment analysis, although I'd have difficulty explaining it just because I've seen this problem so many times and now I see it as a weighted average kind of a problem. But you see with this formula for the centroid of the quarter circle, once you find the distance, then you multiply that distance, we're referencing from the left edge, by the magnitude of the force, whereas for F sub v, it's 1 meter from the left edge. And so it's going to be not in the middle of the two forces, but a little bit more towards the 1 meter side of things. And so when we do that weighted average, we get 0.957 meters. I wish that this was the least ugly geometry we're going to look at today, but it's not. Actually, the next example is just a real hot mess. It's a disaster. So we need to preserve a little bit of time to look at that example. Any quick questions before we move on to the next example, which I've prefaced as a disaster? Talk about poisoning the well. Yeah. No, I guess not. What is the point? Just so that we know how to do this sort of thing. Yeah, good question. You should always ask that question. What's the point? For everything you do. Yeah.
Is there a standard like labeling convention for this, like YCP is center of pressure? Is there a standard like that?
XCP. So when we're talking about like the resultant vertical force, I'll measure some distance and often calling it XCP. And I think in the next example, I use that notation. Great question. All right. Here's a shape. It's a curved gate. Again, it's got some distance into the page. So it says it's 4 meters wide. So this one's convex. The other one was concave, right? Have I used those words correctly? Okay. So this one's convex. Now, what's the basic procedure for these? We found the vertical forces, which is the weight of the water above the gate. We can do that. And then the horizontal force is the force that's acting on the vertical projection. What is the vertical projection of this curved gate? What is the dimensions of it? Yeah, go ahead.
Oh, no, I was like picturing.
Ah, you're picturing it. Good. It's a rectangle. What are the dimensions of that rectangle? 3 by 4. So the rectangle is 3 meters tall and 4 meters wide. That is, like if you were going to shine a light on that curved gate, its shadow would be 4 meters wide and 3 meters tall. Okay, so if you're already starting to think about how you're going to break this down, the horizontal component part, easy. The geometry of the weight of the water, also easy, but it's going to take some finesse, all right? So the finesse we're going to use here is, let's say we've got these two shapes. We've got shape A and B. And the reason why we're doing this is in the back of your book, there's no formula for the area. You can do the quarter circle, right? But what's left over when you subtract a quarter circle from a rectangle? Anybody know the name of that shape? I think it has a name. I don't know it. But we can derive on our own what the area of this piece is and the location of the force. We can do it through a little bit of basic analysis. And so check out this high-grade animation. We've got element B. Everybody understands that element B is just, it is where the water would be if this gate wasn't in place. It would be down to the bottom edge, and so it's a rectangle that goes from A over here to this bottom right edge, up to B, and then over to the top left edge. That's what this B is. So now we've broken that overall piece of B into two parts. There's C and D. D is a quarter circle, which we know how to find the area for. We know how to find the location of the force for a quarter circle, but what we don't know is the area or the location of the force for this element C. And so we can do it by like superposition and subtraction. So, right, back and forth so many times. Finally, it'll start to dawn on you what we're trying to do here. So the reason why we bring it up is that we have to find the magnitude of the vertical forces. That's one half of the equation, the magnitude of the horizontal force, then the magnitude of the vertical forces. So the vertical forces acting on this gate is element A, the weight of the water in element A, which has a depth of 4 meters from the problem statement? Yeah, 4 meters. So element A is 4 by 2 by 3. And then element C is 4 meters wide, but we're going to have to find the area some other way. All right. So here's our formula for the weighted average, how we're going to find the location of that force. All right. So you know the procedure. I'm going to pause the recording for a bit and give you some time to try and tackle this. Start with the horizontal force. That's the easy one in this problem, the horizontal forces. And then move on to the vertical force components. Force of component A, force of component C, and then see if you can make any sense of where those forces are located. The horizontal is the easiest place to start on this. So the projection of the gate is 4 meters wide and 3 meters tall. And just because I know I'm going to need it later, I calculated the area moment of analysis. So the depth of the centroid is going to be 3.5 meters. Let's go back to the drawing here. So the middle of this vertically is 1.5, and then from the edge to the water surface is another 2 meters. So that's why it's 3.5 for the delta H. Okay, the vertical projection, horizontal force. Yeah, I do too. So then the YCP, thankfully it's the easy situation since it's vertically oriented with delta H and Y bar the same. The hard thing is the vertical forces. The magnitude's easy enough. Yeah, that's what this approach is showing. No. Yeah. For the YCP? Yeah, 12 meters. Yeah. The magnitude of the forces is easy enough, right? It's just the weight of the water. So if you can find the volume of the element, all you have to do is multiply the volume by the unit weight of the liquid. So the element A is just a rectangle, and it has a shape of 2 by 3 by 4. So A, just to refresh your memory, if you go back here to the view of it, it's that rectangle that's above the water. Above the water that's immediately above the gate. And then element B is the overall, distance from here is B. And then we break B up into the two pieces, which are C, which is the actual where the water is, and D is where the water isn't. It's the water that's being held back by the gate. Okay, so back to the solution. Give you a few minutes for this to soak in like a stain on a carpet or something. The vertical force location. Well, it's just the same thing we did before, the weighted average. So we know that the overall area of the shape is 36. And we know, yeah, right, the volume of this cube here of cube B. And we know that B, the overall force is going to be in the middle. So the overall middle is defined by the location of the two pieces, piece C and piece D. So it's, in this case, we know the average, and we know this piece, and so the only thing we don't know is the location of C. Yeah, right. That's right. So this vertical force location, what we're solving for is the one force location we don't know, because we know that B is the combination of element C and element D together. And so here is the that small sliver shape, which is element C. We're calling this C. Right? C is the leftover. When you have B as the main overall rectangle and subtract out the quarter circle. C is what's left over. And so we can know the location, the distance to the force from the edge. And then we can also find the area and solve for the unknown force location. So this is a tricky one, but again, just to repeat it, we know that the force, if there was water in all of B, the force would be 1.5 meters from the edge, if it was full of water. But it's not. And so this resultant force here is going to have two components. It's going to have the component of where the water isn't, and we know the formula for the XCP of that. We don't know the distance, how far from the edge it is to where the water is located. And so finding the location of this unknown, we can get from breaking up the overall entire location B into the two segments and using the weighted average approach. That's what this is just sort of the result of a weighted average where we know the size, in this case volume, and the location of the resultant, and one of the components, but the other component has a force location that we're trying to find. Don't start getting depressed if the geometry of this is what threw you off. If the underlying approach of how to solve the force of a curved gate is with you, then that's what's important. And I'll illustrate that by giving you the key ideas of two problems that are on your next homework assignment. Before I launch into those key ideas, anybody have a question they'd like to ask for this example?
I got one.
Sure.
So for the area right above the gate,
Mm-hmm.
this curvature, you're saying that we find the volume of water that's not there, the volume of the water that is there. and
That's
we
right.
subtract the two?
Well, not that we yeah, okay, so I'm saying like B, we can easily find the volume of B, right? It's 3 by 3 by 4. And then you're subtracting the volume of this pie-shaped element, and then that's what gives you the volume of C. Yes. Right. Other questions? All right. Well, if you want to ponder the mysteries of this example, the solution is in the recording, the YouTube recording, so you can go to that. Let's take a look at some of these upcoming homework problems then. All right. Sometimes we're going to be finding the weight of the water that's there. That's what this drawing is showing, is that sometimes the gate, it has water directly above it, and sometimes the gate has water below it. You see this picture on the right. It's not about the water coming from above, but it's the water from below that's causing the hydrostatic force. And so one of the key principles you're going to have to know for these homework problems is that the magnitude of the vertical force is either the weight of the water that's above the gate, you've already done those, or the weight of the water that should be above the gate. Because in this picture on the right, there is no water above the gate. But how much water would be above the gate if this gate wasn't there? So that's what this dashed line is representing, is, there's a certain volume of water that is being held out of the way because of that gate. And so the key idea here is that you can find the vertical force on these problems that is either the weight of the water that is above it or that would be above it. So with that idea in mind, consider this problem. This is one of the problems that you have in your homework. And you're going to do the horizontal forces and the vertical forces in the same two steps that you've done for both of the examples today. The vertical forces, it's not about how much water is above the gate, it's about how much water should be above the gate. It's just similar to the slide that I showed you previous to this one. And so there's a quarter circle, and then there's a rectangular component. You can break it up into the two pieces and then ask, what would be the weight of the water above this gate if water was in place. And so that's how you can find the vertical forces. The horizontal forces, you're thinking about the projection of the shape. And this is a flat gate that was curved, and so the projection of it is just going to be a rectangle. And if L is 1, then that tells you the height of it is 1, and I don't remember exactly how far into the page. Oh, I don't remember how far into the page. 1 meter long. There it is. Okay, so L is 1, and then it's 1 meter long. And so that 1 meter long is saying the component into the page is 1, and since L is 1, that means that it's going to have a square shape. The vertical projection is going to be a square. So you'll find the horizontal forces by finding the depth to the centroid and that same approach we've done previously. Okay, this last one, remember that the projection of a sphere is a circle. And so this is a hemisphere. The projection of a hemisphere is also a circle. If you look at the head of a circular bolt from the front, it looks like a circle. And the top of the bolt is similar to what this is. It's a plug that's holding water back. And so I have given you the volume of a sphere formula there. This is a hemisphere, meaning half of a sphere. So the horizontal forces, you're just going to pretend like it's a circle in the water at a certain depth. And so you're going to have to find the location to the centroid, use the area moment of inertia formula to find the YCP, in other words, the depth of the centroid, which is where the horizontal force is located. But then for the vertical forces, it would be really hard to find out the weight of the water that's above this object. So the easier thing to do is to find out how much water is the object holding back. Similar to the previous one where it was about not how much water is there, but how much water is not above the gate because the gate being in place. And so this plug is displacing a certain volume of water. And if you find the volume of water that this plug is displacing, then you can know the vertical forces that are acting on the plug. Because the vertical forces are just reacting to what the plug has done to the liquid. All right, so I hope both of those hints are helpful. That's all we've got for today. I'll see you on Thursday or tomorrow in lab if you're in my lab group. Have a good one.